Okay, so next let's have a look at this thing called an inverse of a 2 by 2 matrix. Well, let's first just think about our normal numbers, our number system, right? So last time we said that 1 was the multiplicative identity because any number times 1 you will get back the original number. So for example, 5 times 1 is 5 and 1 times 5 is 5. So we say that 1 is the multiplicative identity because whatever you multiply a number by with 1, you always get that same number back. So when we talk about inverses, we're really asking, well, for example, 5 times what give me back the identity, the multiplicative identity, because I'm multiplying. So 5 times, so you're really thinking about 5 times what gives me 1. Now, in normal numbers, we know that the opposite of multiplying is dividing, and the easiest way to work out that unknown is to divide, so we know that that unknown is 1/5, or sometimes we might even write that in index notation as 5 to the negative 1, because that means 1 over, right? So that 5 times 1/5 gets me back 1, which is the multiplicative identity. So that idea of 1 being the identity, the multiplicative identity for numbers, it's similar to how the identity matrix is the identity for matrices, right, for multiplying, because anything times the identity matrix, you get itself back. This inverse, we're asking, well, a matrix A times what gets me the identity matrix back? Sadly, while we can just go 1 over or just divide by the number 5 to get 1/5 as the answer, as the inverse of 5 for multiplying to get back the identity 1, that doesn't really work for matrices because there's no such thing as dividing matrices. So instead we use this thing called inverse, which is, it looks like a similar notation, but the idea is slightly different as well. So definition for a square matrix. So it only works for square matrices. The multiplicative, that's a typo. That should not be identity. It should say inverse. The multiplicative inverse is called the inverse matrix. Notation, we denote it with A inverse, A to the negative 1. It does not mean 1 over A, okay? Be very, very careful. A inverse does not mean 1 divided by the matrix because that does not make sense, okay? You cannot divide matrices. But the idea is if you multiply A by this A inverse, so just like how 5 times 1/5 or 5 times 5 to the negative 1 gives you 1, A times A inverse should get you back the identity, and the same as A inverse times A, because that's the point of inverses, is that whatever you multiply by the original, you get the identity back. So again here, very important, you cannot divide matrices. Instead, we have this magical formula, very, very important. For a 2 by 2 matrix, A, B, C, D, the inverse is defined as 1 over det of the matrix, which is what we worked out before, AD minus BC. Now, be very careful. It's also a 2 by 2 matrix, so you switch the positions of your D and A. So do a switcheroo along your diagonal, and you negative your B and the C elements. So if you don't like the 1 over det A, you can just replace it with the det A formula, which is AD minus BC. Again, switch your A and Ds and negate your Bs and Cs. So notation-wise, we do use A to negative 1A inverse, just like we would with 5 times 5 inverse gives me back my multiplicative identity of 1, but you cannot divide matrices. We use this magic inverse formula to make it work. So example 8, let's apply this. So work out the inverse of this matrix B and then verify that the inverse does work and check that when you multiply it works out. Okay, so let's start with default formula, so at least you can get some sympathy marks. So by definition, A inverse is 1 over det A, switch your D and your A positions, and negative your B's and the C's, where your determinant is AD minus BC. Alright, so get some default formulas going. Let's actually apply to our matrix B. So our matrix B of interest is 2, -1, 3, and 5. Let's do it step by step. I mean, you can do it all in one go. The determinant of B is AD, so 2 times 5 minus B times C, so 3 times -1, so that's 10 plus 3, so that's 13. So B inverse is 1 over the determinant, which is 13. It will become a 2 by 2 matrix. So switch your A and D positions, so 5 and 2 switch, and you negative the other two entries, so it'll be -3 and a +1. So therefore, that's your B inverse. Okay, so let's check. If I multiplied B and B inverse, will I get back the identity? So B was 2, -1, 3, 5. I need to multiply that by 1 over 13, 5, 1, -3, 2. So the 1 over 13 is a coefficient, it's a constant, so I can multiply that out later. I'm going to multiply my matrices first. So I've got a 2 by 2, and I need to multiply by a 2 by 2, so I should get back a 2 by 2 because the inside dimensions match, and I should be getting the outside dimensions as my final answer. Okay, so let's multiply. So 2 times 5, so 2 times 5 is 10 plus 3 gives me 13. Row by column, so row 1, column 2. So 2 times -3, -6 plus 6 gives me 0. Row 2, column 1, so -5 plus 5 gives me 0. And row 2, column 2 gives me 3 plus 10 is 13. So now I multiply that 1 on 13 outside the coefficients. Remember, if you're multiplying by coefficients, every element inside is being multiplied by that coefficient. So 1 on 13 times 13 is 1 and 1. So there you go. B inverse is the identity. That's good. And we need to check that B inverse B is also the identity. So let me just shrink this a little bit. There's enough space. Okay, if I shrink that, that should give me more space to do B inverse B. So same thing, B inverse we said was 5, 1, and -3, 2 times original B is 2, -1, 3, 5. So I'll do the coefficient 1 on 13 last. So row by column, row 1 by column 1 gives me 10 and 3 gives me 13. Row 1, column 2, 15 minus 15 is 0. Row 2, column 1 gives me 2 and -2 gives me 0. And lastly, row 2, column 2, 3 and 10 gives me 13. If I multiply the 1 on 13 through everything, because it's a constant, I do get back my identity. So therefore, this B inverse does truly satisfy the definition of an inverse, which is where regardless of which side you multiply the inverse of the original matrix, you should get back the identity matrix.